Hello, everybody, and thank you for taking the time to join this session. This is Davide Gandino from Sky Italy. I lead the streaming, cloud, and computing system engineering team in Sky Italy Technology Department. I would like to introduce you to a very interesting project we are running in Italy, the new disaster recovery project, also known as Fenice. Let's start from who I am. I am a telecommunication engineer. I've joined Sky in 2013, following some previous experience in Liberty Global and other small system integrators. I'm expert in video, with a stronger expertise in video streaming and the infrastructure that supports the video workloads. I am trying with my team to fill the existing gap between the development domain and the video domain, applying DevOps principles to video. Hopefully, you'll see later what I mean. Let's see what we are going to cover in this session. After an unfortunate fire into our Rome data center, we needed to raise from ashes, just like the Phoenix, and redevelop our DR capabilities. We took a chance to develop an innovative hybrid platform that supports our multi-platform delivery. We'll have a look at the scope of the project, its timeline, then we have a look at the approach we have taken, the so-called red button approach. Finally, we'll have a drill down on the new platform design and a short video. I hope you enjoy it. Let's start with the very beginning. On June 13, 2019, we had a fire in our Rome data center that basically took our local office down. In those hours, we started the DR process and we rebalanced all the services in Milan. Good news was that we've managed to have a near zero impact on our customer base. As said, just after the fire, we managed to launch the DR process and we rebalanced all the services across Milan's data center. Just after that, we put in place a mitigation plan. Then we got this project approved, so we started to work on it. We designed the solution, we started the development phase, and we are now in the integration phase. We soon start end-to-end phase testing, and we aim to go live in Q1 2021. Let's have a look at the scope of this project. We need to encode 117 linear channels, of which 78 played out by Sky and 39 third-party pass-through. We need to handle 4 different encoding and distribution platforms: satellite, DTH, digital terrestrial television, IPTV, and OTT. Those platforms sum up to roughly 800 cloud encoders needed to support the multi-platform delivery. We'll ingest 4 gigabit per second streams to the cloud and will download up to 8 gigabit per second from the cloud. VOD is indeed in scope as well. We will have our hyperencoder as a service to encode 12K assets per year. Everything will be run in 5 points of presence, amongst which 2 public clouds. We'll see some detail later about this. At the bottom of the slide, you can see in evidence the components and scope of the project. Basically, from the playout to the transmission and delivery of the linear channel and VOD assets. In particular, this session is focused on the processing and distribution components. So, what is the approach we have taken for this new DR solution? We like to call it red button approach. This means that we have designed a system that doesn't require any human intervention other than launching the DR activation. Actually, a physical red button will be present in our Rome facility, and our operators will be able to kick off the DR automated process pressing it. In the unfortunate case, it will be needed. What are the key implementation pillars that we have followed to design this solution? First one, every component shall be automated. As said, we expect zero human interaction and zero reconfiguration effort. Second, the component, when possible, shall be software defined. Of course, there are components that are not available in software, such as DVB-S modulators, high frequency components, etc. But everything else shall be software. Third, the components, if possible, should be distributed. In those months, we managed to design the components that can be distributed in order to absorb the loss of one site, sometimes leveraging on public cloud. Fourth, the DR should be synchronized with the business as usual configuration. Every configuration change shall be reverted into the DR config, all in an automated way. Last but not least, every component shall be observed. Our goal is to have the same or better visibility than the actual production when the system is active. Let's see a very light architecture. It's just to provide you a sense on what are the locations involved in this project. I've mentioned before the 5 points of presence that play a role in the finished project. The first one is Rome. We host there a data center with our conditional access headend, our high-frequency components that are needed for DTH and DTT deliveries, and the Tier 0 playout. In Rome, we host as well a part of the operations center and their monitoring tools. Then let's move to Milano Caldera. It is an internet exchange POP. We host there the SRT gateways needed to ingest linear streaming to the cloud. Then we host there the cloud interconnects to reach Amazon and Google. And then we lastly host there the IPTV and OTT caches that are needed for CDN cache fill for OTT IPTV deliveries. Then we have a third-party location that supports our Tier 1 channel playout. From there, we contribute the streams to Caldera and then from Caldera to the cloud. Lastly, we have the two public clouds. There, we host our multi-platform encoding stack, the video on demand components, the DRM components, and some other ancillary components that are needed to have our stream working end to end. The last bit that we host there is the Tier 2 channels playout. We've just mentioned the public cloud. We managed to build and configure on demand all the components that lives there. Then we destroy them when not needed anymore. This is possible thanks to a component called SCL, Service Control Layer, which is responsible for keeping the DR configuration aligned with the production system. SCL is also responsible of mapping the configuration of production system with the component chosen for the DR project. This is needed because not always the components present in production are the same present into the DR, so we need to map the different technology stacks accordingly. This is of course done in an automated way, and it is crucial to have configuration consistency into the DR platform. The beauty of this on-demand approach with the public cloud is that we have a near zero cloud footprint when the DR is not active. The amount of money we spend on cloud to keep the DR in a ready-to-be-launched state is very low if you compare to the cost of an always running DR. We talk about some repository plus a couple of VMs. Let's take a closer look at the DR activation process. The operator presses the now famous red button that triggers a script. The script is called Diavolina. It is a commercial name for a famous lighter cube in Italy. Well, this time at least is a more pleasant fire. Diavolina is responsible to deploy the first Kubernetes cluster, the management cluster, that will deploy all the other infrastructure via some Jenkins jobs. Those Jenkins jobs are called barbecue, and they will be deploying 13 Kubernetes clusters across the two public clouds, a bunch of VMs and some databases. The second step is to deploy all the application on the just created infrastructure. Last step, of course, is to configure all the just deployed application. And of course, the on-premise component accordingly will let us DR configuration on the repository. Everything here is done using Pulumi as the Infra as a Code SDK, Jenkins as the deployment engine, and the majority of the workloads here lives on the Kubernetes clusters. Now it is time for a live demo. You will see in seconds an accelerated video. The goal is to provide you a feeling on what's going on in case of DR activation. The actual focus will be on linear channels only. An issue has occurred in our Milan data center, and we have the systems offline. As you can see, nothing is present, neither in GCP nor in AWS. Our customers get error messages and simply can see their preferred content. The DR plan is asked to be activated. The operator presses the red button that triggers the Diavolina script. Diavolina kicks in and starts the creation of the management cluster in GCP. The management cluster is scaled up, adding more node to it. The DNS server is configured and host names are registered. Jenkins is deployed while secrets and dependencies are sorted. As soon as Jenkins is ready, some seed jobs are starting. These jobs are the so-called barbecue pipelines. They are responsible of the creation of all the other clusters, VMs and databases across the two public clouds. Let's see how many Kubernetes cluster barbecue creates. The first one is the general purpose cluster in GCP. Then we have two clusters for the DTH and DTT encoding platform in GCP. Then we have two clusters for the OTT encoding platform in GCP and two other in AWS. Then we have two encoding platforms for IPTV in GCP and two in AWS. Lastly, we have the last cluster, which is the cluster for the VOD content processing and DRM headend, which live in AWS. You might wonder why two encoding platforms for any specific distribution platform. It is because we encode the content twice in different availability zones in order to have a full and seamless redundancy. You also might wonder why two public clouds. This is driven by content proximity and minimization of the egress. As said before, the tier 2 channel playout lives in AWS, so we encode those channels there. One of the beauty of this deployment is that the encoding stack is the same for all the different distribution platforms. The differences are just in the deployed pods and their configuration. You'll see that it will take some time to build all the cluster. And actually that's the most disturbing thing, because we need Google and Amazon to cope with our request. As soon as the clusters are ready and scaled up, by the way, we create them small and then we scale them according to the workload. This is done to gain some time. We start the installation of the application stack. We do it using the Kubernetes operator framework that is responsible of this bit. It installs the encoding platform, the origin servers, the DRM components, and other components that are needed to support our linear channels on their distribution platform. After the apps are deployed, it is the turn of the channel configuration. Again, we do it leveraging on the Kubernetes operator framework, all in a declarative way. That means that everything in barbecue is idempotent and easily reproducible. After this, barbecue install all the remaining components needed to have the full end-to-end ready, common scheduler, monitoring tools, and so on. Last step is the configuration of all the on-premise components as well, such as conditional access maxes, modulator, caches, in order to be DR ready. Then we deploy components that are needed to support the operation in the coming days after the disaster. As you can see, we receive Slack notification on the status of the channels by the monitoring tool just deployed. When all the config is done, eventually the channels are back online and our customer can see again their preferred content. Here in the last bit of the video, we just see that the command scheduler has started to produce event-based playlists to support the restart capability that we have on our clients. Thank you for taking the time to join this session, and please feel free to raise any question that you might have. I will be more than happy to reply to those. Thank you so much.